Hello and welcome to this tutorial on Safety Risk Mitigation, SRM, using the Hazard Identification Risk Mitigation, HIRM framework. I'm Nit. In this session, we'll walk through how to identify, assess, and mitigate aviation hazards step by step with SRM tools. I assume you all have a knowledge on Safety Management System, SMS, particularly on hazard identification. In order to fully understand this session, this is due to the overall intent of a safety risk mitigation process is to drive the risk index, RI, of a consequence to as low as reasonably practicable, LRP. This can be achieved through enhancement of barriers, defenses between a given hazard and its credible consequence. Like what you see here is the hazard, unsafe event, and ultimate consequences. Let's begin with a simple idea. Does this table look familiar to you? Yes, this is a safety risk tolerability table, the end result for SRM. Giving an example here, you got 3C, risk index, which will be indicate as tolerable. How did you got 3C equals tolerable? By having this step here first. Take a look at this 2 table here, severity table with the meaning and value from negligible to catastrophic, E to A, and likelihood table from extremely improbable to frequent, 1 to 5. Therefore, based on the severity value of C and likelihood, value of 3, the result of risk index will be 3C Charlie, which is often based on the group of people or SRM team judgment in comparison with the meaning provided in each table, severity and likelihood. Actually, this process above does not in depth explain the figure and the end result in detail. In short, we call it gut feelings by comparing the meaning stated on each table. Often we also have the tendency to assign desirable, low likelihood values, regardless of barrier strength, results in risk index with unauthentic, artificially low likelihood values. Yes, this is quite a challenging process. Although the process of assigning a severity value is based on the nature and description of the consequence itself by correlating it with the given severity table. This is a straightforward process. Example, when the aircraft crashes on ground, the severity is catastrophic, multiple death, total destroyed, etc. In other words, the severity justification will always be the same with whatever the event projected. The real challenge is to choose the right likelihood value for a consequence that is often unclear and subjective. In reality, likelihood is closely linked to how strong the barriers are between the hazard and the outcome. So how do we do that? Since there is no clear method in SRM to decide how likely a consequence is, especially based on the barriers in place, here is the method that could be beneficial based on what has been practiced and taught on. First, International Civil Aviation Organization syllabus on HIRM training package. Second, HIRM journal by Mr. Theo Kim Tong, Principal Training Specialist, Safety Management, Civil Aviation Authority Singapore. Third, Civil Aviation Authority of Nepal, First edition, July 2018. Fourth, SMS Implementation in Part 145, AMOs, FS1 Maintenance and Production Department, 24 November 2023, Sharing Practice by Mr. Alberto Nozal Camo, MOA expert. Those training packages, journals, write-ups including presentations are addressing the systematic SRM tools. Let's start with the likelihood. The objectivity and consistency in determining the likelihood value are enhanced through the application of the Consolidated Barrier Strength Value (CBSV) methodology. CBSV process provides the assignment of an individual barrier strength value BSV to every single barrier defense between the given hazard and its consequence. First, list 9 barrier quality elements BQE. This can get it from CAGM 1902 SMS 8.7.4. Number 1, effectiveness. Number 2, cost benefit. Number 3, practicality. Number 4, acceptability. Number 5, enforceability. Number 6, durability. Number 7, residual safety risks. Number 8, unintended consequences. Number 9, time. The explanation of each barrier can also refer to CAGM 1902. Always remember, the effectiveness of each alternative strategy must be evaluated before a decision is made. How? Each preventive control should be evaluated based on the 9 element by giving each of them with the score. Let's call it as barrier quality element, BQE, score criteria. The barrier quality scores start from number 1 to 5, poor to excellent, and here is the score sheet for each element, 9 which mentioned earlier, score calculation. Add the scores for each of the 9 barrier quality elements. Example, effectiveness, cost benefit, etc. across the columns for a particular barrier. This total score is the total barrier quality score. Next, use the correlation table here, barrier quality to BSV correlation. Match the total score to the corresponding BSV score range. The BSV barrier strength value range, example 9 to 15 equals BSV, 1, 16 to 22 equals BSV 2, etc., is derived based on how the barrier quality elements, BQES, are scored, and it provides a way to convert total quality scores into a standardized strength level, BSV. Here's how the range is determined. Explanation of the number for the table presented earlier. There are 9 barrier quality elements, BQEs. Each element can be scored from 1 to 5, typically. 1 equals poor, 2 equals fair, 3 equals good, 4 equals very good, 5 equals excellent. Minimum total score equals 9 if each BQE scores the lowest value 1 point. Total equals 1 times 9 equals 9. Maximum total score equals 45 if each BQE scores the highest value 5 points. Total equals 5 times 9 equals 45. To make the total scores meaningful and easier to interpret, the full score range 9 to 45 is divided into 5 bands, each representing a BSV as per the table here. Why these ranges? The ranges are approximately equal in span, 7 points each. This allows a simple, consistent mapping from total quality score to a BSV value. The BSV range, 9 to 45, is split into 5 categories to rate the strength of a barrier from very weak, BSV 1, to very strong, BSV 5. It transforms qualitative scoring into a quantitative value for easier comparison and risk decision-making. Next, we talk about Optimum Consolidated Barrier Strength Value, CBSV. This is used when the number of barriers exceeds the recommended or optimum number of barriers, ONB, for a given risk level, from optimum number of barriers and applicable CBSV likelihood tables. To calculate this, select only the highest BSVs equal to the ONB. For example, if the ONB is 3, you select the 3 highest BSVs. Example 4, 3, 3. 2 number of BSV are 4, choose highest BSVs only, exclude 2 the less effective and only calculate 4 plus 3 equals 10. Now the next question will be, how did you get the ONB number? We revert back the process and look into this table called Optimum Number of Barrier and Applicable CBSV, likelihood here. This table shows the optimum number of barriers, ONB, required for different severity levels of consequence, ranging from E, negligible, to A, catastrophic. Why the number of barriers starts at 2 for severity level E. Even when the consequence severity is negligible E, there is still some level of risk involved. At least 2 barriers are required to ensure that there is redundancy. If one fails, another remains. Starting with 2 barriers reflects good risk management practice and avoids over-reliance on a single control, especially in aviation line. So here is the logical progression from E to A, severity. As seen in the table here, E required barriers, OMB 2, minimum baseline safety, D required barriers, OMB 3, slight increase in risk, 1 extra barrier added, C required barrier, OMB 4, significant consequences need stronger defenses, B required barrier, OMB 6, high risk events needs robust layered defenses, A required barrier, OMB 8, highest risk, maximum safety layers required. Next, we talk about how to derive a likelihood value based on the Consolidated Barrier Strength Value, CBSV, for a given severity level of consequence. We saw this table earlier where the last column is applicable CBSV, likelihood correlation table, meaning if you got any of the severity level of the consequences, the applicable CBSV for likelihood will also follow through. So here is the table from table 4I to 4V. Each of the table has ONB and MAX CBSV. Now, how the figures and number ranges are calculated for each CBSV likelihood correlation table. First, identify the severity level. Each severity level, from E, negligible, to A, catastrophic, corresponds to a specific optimum number of barriers, OMB. Maximum possible CBSV equals OMB times 5 because each barrier has a maximum BSV of 5. Calculate the max CBSV highlighted on the table here. Second, divide max CBSV into 5 equal bands. Each table then splits the full CBSV range from 0 to max CBSV into 5 segments, each corresponding to one likelihood level here. Allocate CBSV ranges to each likelihood level by given table 4I to 4V. Example, table 4I. ONB equals 2 and max CBSV equals 10. CBSV range 0 to 10 and 5 segments. Each segment covers about 2 points of CBSV. The rest will follow the same process. Lastly, we need to understand the severity assessment, how to assign the severity fixed by consequence type. Assigning a severity level is primarily a straightforward judgment based on the nature of the projected consequence, especially when dealing with high-impact events such as aircraft accidents. For example, in the case of an aircraft crash with loss of control during takeoff or landing, the severity is typically classified as catastrophic, level A, due to multiple deaths and aircraft destruction, regardless of any minor contextual variations. This already mentioned earlier in this video, we need to always remember that the final severity is a straightforward judgment. However, the numerical scoring helps to justify and support the assessment more objectively. Here is the process, how to get the severity score. We need to identify the unsafe event or consequence projected. When we have this, then we need to assess the impact. How? We can use these 7 impact areas here. Let's call this impact score to severity value correlation. There are 7 areas such as number 1, passenger, public, safety. Number 2, employee, worker, safety. Number 3, product, service, quality. Number 4, asset, financial, loss. Number 5, reputation, loss. Number 6, aviation security, breach. Number 7, environmental, damage. You may refer to each explanation in the table here. Of course, we need use the impact levels table to assign a score from 0 to 5 based on severity in each area. Each of the 7 impact areas has a specific weighting factor, in brackets, refer to the score sheet here. This factor reflects the relative importance or criticality of each area to the organization or operation. Multiply the score by the area's weight. Example, passenger public safety times 4, worker safety times 3, product service times 2 and others times 1. Here is the logic behind the weighting factors. The logic is to prioritize the impact areas based on their potential consequence, severity to aviation safety and operations. Time 4, passenger public safety. Highest priority that harm to passengers or the public is the most severe outcome, aligning with International Civil Aviation Organization, ICAO, and local civil aviation safety focus. Time 3, employee worker safety. Also critical. Injury or fatality among crew or ground personnel has major implications. Time 2, product service quality impacts to airworthiness, operational reliability, or customer-facing service quality, moderately significant. Time 1, financial, reputation, security, environmental. These are still important but have less immediate or catastrophic safety consequences compared to life safety. To get the consolidated impact score, add all the weighted scores, and for consolidated severity level, use consolidated impact score to severity level correlation to map the total impact score to a severity level. Here the explanation of the next table, consolidated impact score to severity level correlation. The Consolidated Impact Score to Severity Level Correlation Table shows how a numerical score derived from evaluating multiple impact areas translates into a severity level, A to E. Here's how each number range, 1 to 65 in the table is determined. Maximum possible consolidated impact score equals 65, minimum equals 0 score bands and severity levels. The ranges are approximately equal in span, 12 points each. About impact score, resultant severity. The impact score, resultant severity, is generally fixed and rarely changes once the consequence is clearly defined. This is because the projected outcome, exemplify multiple fatalities, aircraft destroyed, remains the same regardless of when, where, or how often the same type of consequence occurs. Therefore, a projected crash will always result in high values across key impact areas, exemplify passenger, public, employee safety, product service quality. The calculation helps justify this severity using a structured scoring process, but the severity judgment itself doesn't fluctuate if the nature of the consequence remains the same. I hope this explanation clarifies the logic behind each figure used in performing hazard identification risk mitigation HIRM within your organization more systematically. Of course, there is no strict right or wrong formula. What matters is adapting the approach to suit your organizational needs. However, always ensure that every number used is meaningful and logically connected to the overall process. If you found this helpful, please consider subscribe, like, and leave your comment, especially if this adds value to your organization. Stay tuned for part 2, where I'll walk you through a sample HIRM form and demonstrate how to fill it in.